Hello, students. This is Chapter 6, Chemistry in Biology. In this chapter, we are going to take a look at, in Part 1 of this lecture, we'll take a look at atoms, compounds, and molecules, as well as look at different types of chemical reactions. So today, we're going to kind of review some matter a little bit. Talk about atoms, elements, and compounds. An atom, that's what everything is made out of. Anything you can see, anything you can touch, anything you can taste is made of atoms. They're the building blocks of matter. Remember, in the center of the atom, we have the nucleus. That's where the majority of the mass of the atom is. The nucleus is made of protons, which have a positive charge, and neutrons, which have a neutral or zero charge. Zipping around the outside of the atom, we have the electrons, which have a negative charge. Elements are a pure substance. They are made of only one kind of atom. Every element has a unique name and symbol, and you can find those, of course, on the periodic table of elements. Some of the names match the symbols. For example, oxygen is O, which makes sense. But when you look at, for example, sodium, sodium has the chemical symbol of Na. And you think, well, how do you get Na from salt? Well, Na is standing for the Latin word of natrium, which translates into salt. So some of the elements have some different language backgrounds and roots, if you will, but every element has a unique name and symbol. We can take a look at the periodic table. The reason why it's called a periodic table is because there is a repeating pattern in the horizontal rows. And a repeating pattern in science is sometimes called a period. So the horizontal rows are a period. The vertical columns, those elements are sometimes called a family as well as a group. Just like a family, you have lots of things in common, but each individual is a little bit different. Isotopes are often used in biology. These are special atoms. They're atoms that have the same number of protons, so they're atoms of the same element. They have a different number of neutrons, meaning that their nucleus will have a different atomic mass, and the behavior of the atom itself may be a little bit different. We will be discussing radioactive isotopes a little bit later in this quarter. Radioactive isotopes are very special in that they're really unstable. All of these extra particles they get, they don't like. So they wiggle and jiggle and they try to shake them off. We call that shaking off process the decay of that atom. Radioactive isotopes will give off radiation, and that decay happens at a very constant rate. It's almost like a molecular or atomic clock. So biologists can use the ratio of radioactive isotopes to normal elements in a sample to detect perhaps the age. Carbon-14 dating is a very common type of radioactive dating that's used. Compounds. When we connect two or more elements together, they combine to form a pure substance known as a compound. Every compound out there has a specific combination of elements, and that formula is a fixed ratio of atoms. For example, sodium chloride, regular old table salt. There's one sodium atom attached to one chlorine atom. Together, NaCl. Salt is always NaCl. It is not any other number. It is not any other element. Just like water. Water is H2O. Okay? 2 hydrogens, 1 oxygen. H2O2 is hydrogen peroxide. Adding that extra oxygen on the end makes that substance behave very differently. Compounds can be broken down. They can be broken down into simpler elements. So how do we join these elements together? Well, by chemical bonds. Chemical bonds are the force that holds substances together. You can think of chemical bonds as like the glue that holds all matter together. Forming chemical bonds will store energy for that compound or molecule. When the bonds are broken, then that energy contained in those bonds is released. Electrons are the only subatomic particle to be involved in bonding because they are on the outside of the nucleus. So covalent bonds. Co means together or with. So if you are a co-president or a co-captain of an activity, you work together with the other president or captain to provide your team with motivation to get your goals done. Okay, covalent bonds are electrons working together, bonds that are sharing electrons. Covalent bonds are very strong. Covalent bonds can form molecules. We can have single covalent bonds. You can have double covalent bonds or even triple covalent bonds. The more covalent bonds there are, the stronger that molecule or compound is. Covalent bonds store a lot of energy, but likewise, it also takes a lot of energy to break those covalent bonds up. Ionic bonds. These are kind of the opposite of covalent bonds. An ion is a particle with any type of charge. It can be positive or negative. Ionic bonds are bonds that form with giving or taking of electrons. Ionic bonds are weak. They can be broken apart pretty easily, especially in water. Covalent bonds are very strong. Ionic bonds are very weak. Some of the weakest types of bonds are van der Waals forces. We will talk in a little bit here about hydrogen bonds. A hydrogen bond is a type of van der Waals force. Van der Waals hold an entire molecule. They hold molecules close together. This is how water molecules form little droplets. Every little individual water molecule is attracted to every other individual little molecule. Now, chemical reactions. Basically, what a chemical reaction is where you take all of the atoms that you have and you reorganize them into different substances. A chemical reaction will be different than a physical reaction. A physical reaction would be taking something like ice. Okay? Ice is made of water molecules in the solid state. If you add heat to ice, it melts. It goes from a solid to a liquid state, but it's still water. It's still the same stuff. Chemical reactions, you'll know when they occur because you'll get a change in something that's happening. You can get a change in color or texture. Sometimes heat or light may be formed or be taken away. Sometimes you'll get bubbles, the formation of gases. You can get solids that turn into liquids and liquids that turn into solids with different chemical compositions. That's a chemical reaction. Change has occurred. A chemical equation is a way for chemists and biologists alike to explain what's happening during a chemical reaction. You can think of a chemical equation and a chemical reaction like a marathon. Okay, you have a starting line. Your reactants are your starting substances, okay? The products, that's at the finish line. Those are the ending substances. Now, this chemical race is a little different from a regular marathon. Everybody that's at the starting line will finish the race. However, the order of the runners may be different in the products by the time they make it to the finish line. So you're using the same molecules, you're just rearranging them. Reactants are starting substances, products are ending substances. So, how do chemical reactions occur? There is a minimum amount of energy needed for a chemical reaction to start. Otherwise, we would have spontaneous chemical reactions occurring all the time. And you don't necessarily want that, especially if you're trying to maintain homeostasis. So the activation energy, or the AE, that's the bare minimum amount of energy that you need to jumpstart a chemical reaction. The activation energy is not reached, the chemical reaction will not occur. So we can get different types of chemical reactions depending on what the energy levels are doing. In an exothermic reaction, okay, exo means outside. This is where energy is released. You may see a glowing or light given off. The sample may raise in temperature. So the energy of the products at the finish line is lower than the energy that the reactants had. An endothermic reaction. This is the opposite. Endo means inside. So this is where energy will be absorbed. So the heat or light will go away. The energy of the products then, in this case, is going to be higher than the reactants. Now, enzymes. These are helpers to chemical reactions. Most chemical reactions occur pretty slowly, especially inside our own bodies. We need those chemical reactions to take place right now to get the energy that we need to perform life's functions. So if the activation energy is very high, that reaction is going to take longer to start. So what enzymes do is they kind of act like the biological coach of a chemical reaction. Enzymes will lower the activation energy to get everything going faster. And a catalyst is the substance that actually lowers that activation energy. And enzymes are nothing more than biological catalysts, okay? Enzymes and catalysts are like coaches. They are not directly involved in the chemical reaction. They just get it started sooner and give that reaction the motivated to get completed as quickly as possible. So enzymes are made of two parts. They're made of the substrate and the active site. And those two pieces, once they come together, will lower the activation energy to get the chemical reaction started. That active site and substrate has to fit together exactly. It's almost like a lock and a key. Every active site has a substrate key that will open it. Once, just like a lock, once those two pieces come together, then the lock opens or the chemical reaction happens. Lots of different things can affect enzyme activity. Temperature and pH levels or acidity levels can affect enzyme activity. The warmer things are, the quicker things tend to happen. The more acidic an environment is, the faster things tend to occur. This ends part 1 of chapter 6 lecture notes for the chemistry of biology. Stay tuned for part 2.